Good afternoon, everyone. My name is Priyanka Dewangan. I'm a research scholar in IIT Hyderabad. Today I'm going to present my work where the title of work is Investigation of Etching Characteristic of Silicon 100 Orientation of Paper in Low Concentration of TMAH Solution for MEMS-based sensor. Basically, I'm talk about the fabrication, like how to fabricate the structure, like different type of microstructure. It can be like freestanding structure, diaphragm type structure, cavity, channels that I will discuss about in this talk. These are the content where I will discuss about introduction of MEMS. What is the research came, what is the problem on that, and I'll talk about anisotropic of etching in silicon in low concentration of TMS solution, and I'll talk about result and discussion, and I will conclude on that. And the next is first introduction. Here we know everyone knows MEMS is a like combination of miniaturized electrical and mechanical component on a single chip. Its size in micron to in one chip. In many chip can be comes in a one single wafer. So that MEMS technology developed by the basic three-step fabrication process, thin film deposition, microstructure patterning, and the third is that selective etching of the microstructure. So the we prefer wet bulk micromachining because wet bulk micromachining is a chemical-based process which is a cost-effective and it can be done batch fabrication. At a time, many wafer can be fabricated and also easy to handle. No need to any costly vacuum-based process system we require. And the thing is wet bulk micromachining again is a two type where isotropic and anisotropic. Isotropic, which is based on etch rate is same for all direction. But anisotropic is it depends on orientation of wafer. It can control the etch rate also. Like you can get the slanted plane, vertical plane, you can get on that. Now that in wet bulk micromachining, we can fabricate many of various type of structure. This structure is used in various mesh-based application like freestanding structure that can be used in some sensors, pressure sensor, diaphragm structure is pressure sensor, and there's a many structure we are using for accelerometer, group mass structure. So these are the MEMS-based application where use this type of a structure. So the next is research problem. What is the GAVE? So basically, I'm talking about anisotropic etching of silicon. So these are the etchant which are used in anisotropic agent. So all of them I'm using TMH, tetramethyl ammonium hydroxide. So why I'm using TMH? That is also one more question. Why I'm using TMH first is the CMOS compatible. The second is a high selectivity between the silicon and silicon dioxide. It will etch more and more silicon. The selectivity for silicon is small. And the second is because of the slow etch rate, you can control the etching rate and you can control the formation of cavity or other structure. The same time is a non-toxic and non-volatile because if you are using KOH or NaOH, that will be, it is not CMOS compatible. If you are using ADP, that is a toxic. So the next is why I'm choosing low concentration TMH. The first thing, the etch rate in low concentration TMH is comparatively high compared to the high concentration of TMH, and same time undercutting also. The next is because of the low concentration solution also require less. It will be again the cost effective. The next is most of the study has been performed using high concentration like TMH of 25%. So most of the study they have been used 25%. So very few study have been used a low concentration. So I will explore those study like using low concentration TMH with adding the triton. So I will discuss about why I'm using triton also. So here which is the using silicon anisotropic etching. So here the substrate is silicon 110 where the direction is 110. So the etchant is 1 weight% to 4 weight%. I'll choose in 1, 2, 3, 4. And at the same time, I'm adding the triton 100 ppm. Triton is non-ionic surfactant, which will not react, okay? And the etching temperature I choose in a 70 degree and etching time is 5 hours. For that, these I have to give the detail of composition where I'll mention the name of the what is the composition on that. 1 weight% I mention 1T, and if I add in triton, so I mention 1T plus triton. So at the same time, I'll discuss about the experimental process. As you can see, the silicon, after that I'll deposit silicon dioxide by using thermal oxidation process. For the patterning of microstructure, I coated on photoresist by spin coating process. After that, patterning of microstructure by using the UV lithography process to expose the UV through the photomask to the photoresist coated substrate, and then they have to develop that particular structure and then using the developer solution. We have to do the selective etching. So first we have to remove the selectively on the masking layer, which is silicon dioxide, that is H HFP HF solution. After that, we have to do the removal of photoresist. Why we have to remove photoresist? Because that photoresist, it cannot sustain on that TMAH or any anisotropic etchant solution. So we have to need to remove the solution photoresist by using the acetone. After that, due to removing the acetone, some organic contamination on that we have to remove by piranha cleaning. After this, after during piranha cleaning, some native oxide form on that should be removed by 1% HF cleaning. After this process, we are going for the anisotropic etching by using the 118% TMH with the adding and triton and without adding the triton. And this is the cross-section image. As you can see, like slanted wall we get. So after this complete experiment, we have to characterize on that, like what kind of characterization we have to need. So these are the etching characterization. Yeah, this is the etching characterization. Yeah, fine. It's okay. Yeah, this is the first etching character. I have to do first vertical etch rate. As you can see the figure, vertical etch rate, you can see that after the etching of the cavity, we can get the V shape or truncated shape of geometry. Okay, and you can see same time there are four planes. That is a triple one plane appeared during the etching of 100 wafer, and that will make the angle with the plane to 54.7 degree. Okay, and the same time second is undercutting. Second thing is, why is undercutting you have to measure? To the undercutting, we have to fabricate the freestanding structure, diaphragm type of structure. In same time, and some cases undercutting is required for if you are fabricating the freestanding structure. In some cases where undercutting is undesirable, like fabricating a proof mass structure, mesa structure, on that you are not requiring undercutting. For that case, we are using a triton where the undercutting is reduces very less. So the third is average surface roughness. If we are going to etch the silicon, in same time we get that this type of helix form, a geometry. By it is formed during the anisotropic etching, some H2 bubbles are formed. That H2 bubbles act as a micromass. So form on that, this type of helix shape of geometry is formed. This helix shape of geometry, these are entire surface, is a act as a rough surface. So I'm going to the discuss about one by one etching characteristic. So the first is talk about etch rate and undercutting of silicon. So as you can see, there is a graph which is showing the etch rate and undercutting with respect to the different composition by adding triton without adding triton. So as you can see through that graph, you can see like by adding the triton, that etch rate and undercutting both are drastically changes, like reduces. So it is happened because the surfactant which is absorbed, it is formed on the layer on silicon surface, which is prohibited to where the etchant which have a reactive molecule which is act as a barrier layer, and which is prohibited to react to the reactant etchant to the silicon surface. So same time undercutting also. In undercutting it convex corner where that etchant is this triton is a form as a barrier layer, which is again stopping that etching. So the next etching characteristic is average surface roughness. So as you can see the graph, average surface roughness with respect to different composition of etchant, we can see this bigger size of geometry. So like when you are using only TMH, so they have a like rough surface. You can see these figures. They have a many of hillocks are formed, dense hillocks are formed. When you are adding the triton, you can see that surface is become a very smooth. So this is the thing, like when you are adding triton, the surface becomes smooth. And why it becomes smooth? Because this surfactant molecule is prohibiting to formation of H2 bubble. That's why the surface have become smooth and no hillocks are formed on that layer surface. So in that case, we are getting a very good smooth surface in 40 TR, like 48% plus 100 ppm triton solution, where the surface roughness is 10 nanometer. And this is after 5 hour of etching. When we get complete 5 hour etching, then we get that surface roughness is 10 nanometer. So these all are that. And See, this is the optical image where I'm showing the freestanding structure. So as you can see, this four image. So top of that four image, that is showing like freestanding structure when you are fabricating to the TMA solution. When you are adding the TMA solution, as you can see the bottom images, those are not released because they are very less accurate, as well as same time undercutting is also less. So these two images showing that like first four images you can fabricate by using wet anisotropic freestanding structure, and same time the second bottom row is image you can see you can fabricate that where undercutting is not required. So this is our study. So the next I'm concluding on that is like by adding triton where accurate and undercutting both are decreases, and same time our surfaces become smooth, and this is process is cost effective because we no need any vacuum process, and in this process you can fabricate different type of structure, and it will be get you can get the smooth surface also. I acknowledge to DST Inspire for the financial support. Thank you.